It takes about an hour and a half or so for the recording to get finalized, and then I'll post it online. So the recording should be available hopefully within 2 hours of the end of class, if everything's going well in the cloud where it's being processed. And I'm going to go ahead and start sharing my screen. All right, so right now, can everyone or can people verify, say in the chat, that they can see the PowerPoint slides and that they're seeing, let's see, bring the chat back up here. All right, good. And everyone sees just one big slide and not the presenter view, is that correct? It's in the presenter view, okay. Let me reshare so that I try to get it so that it's a little bigger. Now, back to share desktop. All right, how's that? Can people see just the slideshow? Great, looks good. All right, there's a lot going on my side of the screen. I am going to do my best to manage. If for some reason I don't notice hands going up or chat or whatever, just be patient with me, or feel free again to unmute and call out my name, and then I'll see what I maybe didn't see before. Okay, so let's get started. So so far in lecture one, or E1, we talked about a number of ways to make things more realistic with things like units so I mean, we're primarily focusing on units in lecture E1, and now we're going to move on to delays. We've talked about delays in the form of causal loop diagrams. Oh, and I'm going to actually start a separate audio recording here just as a backup. Great, okay. So we've talked about delays in causal loop diagrams, but we haven't seen how to implement them in stock and flow diagrams, and that's what we're going to talk about today. After this lecture, we'll been done talking about all the basic elements you need for stock and flow diagrams. So from here on out, we will be talking about applications. And so it's very topical. In Thursday's lecture, we'll actually talk about epidemic modeling. It was just already on the syllabus. And so we'll be talking about flattening the curve and all of these things that you've probably seen in the news. And we'll actually see some of the mathematical and computational models that those things come from. And they come from exactly the type of modeling that we're learning about in this class. And so look forward to that on Thursday. And but until we get there, we have to cover delays. And so before I get into that, are there any questions last time about lookup tables? We're going to see them again today, and so I want to make sure that I cover those. Does everybody understand roughly what lookup tables were and how we applied them back in lecture E1? I'll pause a little bit here and in case there's any questions. Okay. Great. All right, so let's move forward then. So delays. So this is a causal loop diagram that we saw when we were first bringing up causal loop diagrams. So this is representing the kind of intake regulation that hunger is involved in. So you are hungry, and so you eat more food, and then as you eat more food, you get less hungry, and so gradually you stop eating and your hunger goes away. So it's a way of bringing your hunger back into balance at zero. But we know that as you eat food, there's some delay into how long it takes until you stop being hungry. And it is this delay with these two little bars marked up here that we're focusing on. How do we implement that in a stock and flow model? And so the questions we have to ask are, what causes delays? what are the types of delays that we can see in systems, and then using information from those two things, how do we then go out building stock and flow models of these delays? What are the tools available for us to model these delays? And so just keeping along with this running example of this ingestion example, if we think about eating food, there are two types of delays that we might consider. And so we'll focus here on what I'm calling fixed delays. And so that's the term that you want to sort of remember, this term, fixed delays. And a fixed delay is one where it takes a fixed amount of time, a constant amount of time to go from one spot to another. So from food to go from the mouth to the stomach. And so if you think about the esophagus, if you eat food, then it's going to take a certain amount of time just to travel down the esophagus. It doesn't matter, it basically doesn't matter up to a certain point. It doesn't matter how much food you eat. If food goes in, whatever pattern that goes into the mouth, you will see that pattern a little bit later coming into the stomach. And there's just a simple delay between them. That's what we mean by a fixed delay. And so in Vensim, there are ways in which we can tell Vensim to add one of these fixed delays. So you could draw, for example, this sort of setup here where I'm going to have a dynamic variable called ingestion rate and another variable called rate into the stomach. And I just want rate into the stomach to be a delayed version of ingestion rate. So in order to get there, I first need to build a model of food being ingested. And so I am going to use a lookup table, borrowing from last time to do that. So this isn't the main focus of this lecture, but it's just showing you another way to use these lookup tables. So remember, I've got this shadow variable called time, and I can bring time into a lookup table. And then if it might be a little small to see, but if you were to zoom in here on the table part of the lookup table, we have various inputs going from 0 to our final time, 15. And then our outputs represent kind of when the food enters the system. And so we're saying at time 5, suddenly we get an ingestion of 5 units of food and it stays in the mouth for a second. And then after that second, it goes back down to 0. So it's like a pulse of food, and that is our model of the ingestion rate. And so what we need to ask Vensim for is, given that we have this intake rate coming in from ingestion, can we build a delayed version of whatever happens at ingestion rate into the stomach that just happens a certain time later? And so if you go into the equation for rate into stomach in this dynamic variable inside Vensim, we can use this function that Vensim provides us called delay fixed. And basically, we've wired up ingestion rate into rate into stomach. So that's a variable that Vensim gives us access to. And we can put that variable first as this argument. And this second argument, I've put the kind of general purpose version down here, is the amount of time we want it to be delayed. And then this last argument, initial condition, is what we want in the stomach before anything's reached it. So we know that when you start the simulation, then basically if the stomach is a delayed version of the ingestion rate, when you start the simulation, we don't know what's currently in the stomach at the very start of the simulation, because it takes 5 seconds for whatever's in the ingestion rate to get into the rate into the stomach box. And so this third one is just, what do you do during that initial wait? And so if I do delay fixed, ingestion rate, comma 5, comma 0, this is a way I can implement that the rate into the stomach is initially 0. And then 5 seconds later, it will be whatever the ingestion rate is from that point on, just delayed by 5 seconds. So let's see how that might look. If I were to then simulate this inside Vensim and then plot these two rates, then I can see the blue rate, that's the ingestion rate, shows up at time 5, and it jumps up to 5 units and then jumps back down to 0 at time 6. And then 5 seconds later at time 10, we see a mirror of that, or we see the exact copy of that. So we've just copied this blue waveform into this red waveform. So just to make that clear, I did not put that funny pulse equation inside the rate into stomach. It is just copying whatever happens at this ingestion rate. And it's just shifting at 5 seconds and putting that, and that's into the stomach. And so how can we use this? What we can do is, so there's just a 5-second delay there, is we can draw a more complicated stock and flow diagram where we have two stocks the food in the esophagus, like, so it's the amount of food that's sort of sitting in the esophagus as it's traveling down the esophagus. And then we also have the amount of food that is in the stomach. And so we can say that the ingestion rate, that's how the food in the esophagus is changing. And the rate into the stomach, that is how the amount of food in the stomach is changing. And so we end up dumping food into the ingestion rate flow, and that is going to be that initial pulse of food. And then while that food is in the mouth, sort of in ingestion rate, it was going then to gradually be shifting into the esophagus. And so the esophagus is then now going to take on all of that food, and it's going to sit there for the whole 5 seconds. And then this rate in the stomach, that will end up 5 seconds later, effectively emptying the esophagus and putting all of that food into the stomach. So if I simulate this, then I get a graph that looks like this one. So now this green pulse, that is my input, my ingestion rate. That's this kind of flow into the esophagus. This blue line is the actual food in the esophagus. So while that rate is positive, this line is rising. But at the point where I stop ingesting, so at time 6, then the esophagus just has a flat value. It stays, it has that amount of food in it. But then 5 seconds later, it hits the end of the esophagus and it starts unloading into the stomach. And that's what this gray pulse is. And this gray pulse, again, is just designed to be an exact copy of the green pulse just 5 seconds later. And that allows the food to empty out of the esophagus and into the stomach. And then you get the end of the stomach. All right, we have a question here. Since we are going to be using all of these factors, delays and others, when constructing our product, are we going to need to explain causality and why it turns out graph the way it does? Well, you need to be able to justify why you drew this figure, or why you drew this stock and flow diagram. So we need to know a little bit about physiology, and physiology tells us that the mouth is connected to the esophagus, and the esophagus is connected to the stomach, and you have to go through the esophagus to get into the stomach. And so that's kind of our limits of causality there. We can say we know that there is a causal connection between what you put in the mouth, what goes into the esophagus, and then what goes in the esophagus and what goes into the stomach. And then hopefully you'll have some, so you could, like, Google for some physiology data, and you'd say, well, I know roughly it takes this long for food to get down the esophagus. Or you could just, say, well, we can, anecdotally, I know that when I swallow, it seems unlikely that it would take more than this amount of time or less than this amount of time. So I'm gonna do a ballpark of 5 seconds or something like that. And so we need some baseline justification for how we built these equations or the expressions. But we're sort of free in how we choose to model it, just as long as we're justified that way. But once we've built it in the model and hit play, Vensim sort of tells us the necessary outcome of our choices in the stock and flow diagram. So it's graphed this way because we've drawn it this way. So as long as we can justify why we've drawn it, we don't need to justify the way it looks. But once we plot it, we can then use that plot and try to then explain, or ask whether it makes sense. And if our graphs don't make sense, we should probably ask, does our stock and flow diagram have a flaw in it? So if you end up, say, for example, I might find that at the end of this, if I were to show that the food in the stomach just keeps on rising and rising and rising, even though the food into the mouth didn't, then that probably tells me that I wired something up wrong inside Vensim, because I should get kind of a conservation of mass. And so then I should probably go back to my stock and flow diagram and figure out if I need to remove a flow or add a flow or change a flow equation. Does that answer your question? With my explanation, we need a research question first and a background story in order to make our model, not based on something we know yet. So yeah, I mean, we have to be motivated by, I would have to be motivated in order to draw this. I might be interested in knowing how does ingestion rate affect the rate of other processes downstream in, say, the in the digestion process. And so, I might know that if I eat, eventually I feel less hungry, but I'd like to understand how, how long it takes for it even be possible for my body to be able to give me those feedbacks. And so that would be kind of the research question that would be going into this, is like, why would I build this model? Is that I want to wire up the few things that I know into a system so that I can then simulate that system and then start understanding how all of these little delays that accumulate add up to the sort of global scale delay of how long it takes for me to start feeling satiated. So that's something we haven't quite talked about yet, but starting next week, when we start talking about epidemic models, that will become much, much clearer. And I think given the surrounding environment with COVID-19, then you've probably, it's actually sort of fortunate that we're going to be talking about epidemic models, because I feel like a lot of these questions about flattening the curve and slowing things down and all that will end up resonating really well with the lecture that we're going into on Thursday. So hopefully it'll make more sense then. For now, I'm just showing you the internals of how to do this stuff inside Vensim. All right. So that's how to do it in Vensim. Any questions about that? Well, I've had that up before I move and show you the same thing in Insight Maker. All right. Great. So for now, I'll move on. If there are questions about Vensim, just feel free to bring them up. All right, so if we want to do the same thing in Insight Maker, and the only reason we don't do this is we don't like Vensim, for example. So if you prefer to do it in Insight Maker, how would we do that? So let's see how Insight Maker has implemented the exact same things. So we mentioned that Insight Maker has these things called converters that basically are where you store these lookup tables. And so we can create one of these converters called ingestion rate, and we can create a dynamic variable called rate into stomach. And if we go into the converter here, instead of creating a shadow variable, time, we can actually say that the input source to this converter is time. It sort of has this internalized shadow variable here. And then we can build the same lookup table that I did inside Vensim. Of course, here, though, I made this go up to 1 instead of 5 units, but otherwise it's basically the same model that I built before. So at 1 second, we get an ingestion rate that pops up to 1, and then at 2 seconds, it pops down to 0. Now, it turns out that I also can implement this without a lookup table. I can use this thing called pulse inside Insight Maker. And basically, I can have a normal dynamic variable, but I can say that I want that normal dynamic variable to implement a pulse at a particular time, with a particular height, with a particular width, and I can specify whether I want it to repeat over time. So as an example, if I do pulse 1110, then I say that this dynamic variable ingestion rate is going to do the same shape as I just implemented in the converter. So this will generate a pulse of height 1 at time 1. It will last for 1 second, and then it'll go back down to 0. And it will not repeat. And so that's a way for me to put that all into one right here. So I can do that instead. And it turns out that actually Insight Maker has the same features. So if we don't like to implement this with a lookup table in Insight Maker, you can actually use the pulse train function in the same way. And it likewise has a start time, an end time, a repeat time. And so you've got all of those things that can be built into here. So that's just kind of an aside if you have to build these things. And you might say, well, why would I want these temporal things? Well, not only do you want to maybe simulate what happens when you eat something at a particular time, but let's say you want to simulate seasonality. Maybe you want to simulate what happens when you get a burst of rain only at a particular time of the year, or a burst of UV radiation, or a burst of demand for a particular product. Then you can implement these things using these pulses, or you can do things using these lookup tables. So that's kind of, again, just an aside. We're really focused here on the delays, but that's how we end up getting these bursts into here, is through either the lookup tables or the pulses. So if I shift my perspective back to rate into the stomach, then Insight Maker also has these delay functions. So over on the right-hand side, when you're editing the equations for these variables, there is a category, historical functions, that has a bunch of useful things in them. And one of them is delay. And so this delay has, you say what variable you want to delay, how long you want to delay it, and again, an initial condition. And that initial condition is optional. If you leave it out, it matches whatever the initial the initial value of whatever the variable you're delaying is. So in this case, if I do the same delay where I just implement delay ingestion rate by 5 seconds with an initial condition of 0, then if my ingestion rate is this pulse, then if I were to plot the rate in the stomach, it will be an identical pulse 5 seconds later. So this is exactly what we just saw inside Vensim. We just get a copy of that pulse 5 seconds later. If I change whatever waveform that I was putting into the ingestion rate, it will automatically change whatever waveform shows up into rate in the stomach. It'll just be shifted 5 seconds later. So now I want to do the same thing I did in Vensim. I want to put it all into a model with stocks and flows. And I have a stock of food in the esophagus, a stock of food in the stomach. I have a rate that changes how much food is in the esophagus. That's my input from the outside world. And so I'm going to eat something at time 1. And then as I eat that thing, it'll end up pushing that food into the esophagus. It hangs around in the esophagus for 5 seconds. And then that pulse that went into the esophagus will become a pulse that goes into the stomach 5 seconds later. And so then that will gradually empty the esophagus and fill the stomach. And so I'm just putting that delay inside the rate into the stomach, and that ends up linking all of this together. So that when I simulate, I get exactly the same plot that I got in Vensim. So I get my initial pulse when I started to eat something at time 5, and then gradually I fill up the esophagus, and then the esophagus has that food in it for 5 seconds, and then 5 seconds after I started eating, then that food hits the stomach and starts emptying into the stomach, causing the amount in the esophagus to go down while the amount in the stomach goes up. And once you've gotten rid of that whole pulse, then the amount in the stomach stays constant. So it's exactly the same as what we saw in Vensim, but we've implemented it now in Insight Maker. So are there any questions about how we did that in Insight Maker? So we just added these functions, delay and delay fixed are the 2 functions we added in Vensim and Insight Maker to implement this delayed version of other signals in the diagram. All right, so now the question is, when would we want to use these fixed delays? And so this esophagus example might be a little bit artificial. So there are a bunch of examples of fixed delays. So any type of schooling behavior. So if there's a tight cluster of, say, animals like fish, so we talk about a fish school. Well, if they move coherently through the system, like a bulb of animals that is just moving through the system, not changing its shape, then we often implement how long it takes for them to get from point A to point B using a fixed delay. So if I will see later on in this lecture, if I want to simulate traffic getting from one intersection to the other, then as they're moving between intersections, I might model them as a group that is moving cohesively together from one intersection to another. Now, if they start spreading out, then that's different. That's the other type of delay that we're about to talk about. Models of age structure. So this is very common. So I might want to model how, let's say you have a cohort. So students that are in 1st grade at a particular time, well, they'll be in 2nd grade. Roughly all of them will be in 2nd grade 1 year later, and in 3rd grade 1 year later. And so you might want to show how a policy implemented at a particular time moves through a system. And that policy might be implemented, let's say, at a particular grade level, but will then have downstream effects as those individuals move to other grade levels. And you might want to follow that through. And so that's another example. So age structure. And that's why you use the term cohort. A cohort are these groups that are moving together. And likewise, students moving through a school system, that's the same type of idea. And then I've highlighted school system here. So it turns out that the word school and school system and the word school in terms of fish actually come from different roots. So one of them has to do with being scholarly and the other one has to do with being in a shoal. But in English, they've converged, and it's kind of interesting because we model them the same way. So we model fish moving from point to point, as we model also students moving as a cohort through a system, at both with fixed delays. And so whenever you see the word school, even though they don't necessarily have the same background, you should think fixed delay. And then anything else, like the esophagus example, materials that flow through systems, transit delays, cars moving through systems, these are all things we model with fixed delays. So any questions there about fixed delays before we move on to our smoothing delays? All right. It's very lonely sitting up here listening to the silence here. I'm very used to seeing your smiling faces. And so the interaction is welcome.
Okay, I have a question. Which Jordan?
Okay.
Speaking.
Hi, Jordan.
So for fixed delays, I know we're going to talk about another type of delay, but with fixed, it's that all throughout the simulation or throughout the model, it's always going to be there. And it's not going to, the delay type is not going to change.
Good question. So you could build a very complicated model that changes its type of delays as you move through the model, but that it would be pretty advanced. I'd say most models, when you model a fixed delay, like the time it takes to get from your mouth to your stomach will always be a fixed delay. And so we might simulate different things going into the mouth or different traffic flows going into the city, but the city will always have a fixed delay between intersection A and intersection B. So because we're in order for that delay type to change, it's almost like the city would have to totally change its infrastructure during the runtime of the simulation, which would be unlikely. Now you could close a road, but you could probably not shift a road from like a car-based system to I don't know, like a transporter system or something like that. So, but the term fixed does not mean it's getting the term fixed just because the delay is constant. And like you say, it'll become clearer what I mean as I talk about the other type of delay. But I'm not using the term fixed because it's the same throughout the simulation, because both delays will sort of be the same throughout the simulation. I'm using the term fixed because we're just taking exactly the shape of something that shows up at one dynamic variable and then copying it to another dynamic variable just by shifting it. We're not changing the shape of it. The pulse looked like a rectangle when it went into the mouth, and it's going to look like a rectangle when it went into the stomach. There are other types of delays, like the one we're going to say, where the pulse might look like a rectangle going into the mouth, but it's going to be smoothed out and kind of lumpier as it goes into the stomach. And that would be one of these smoothing delays that we're about to talk about. Does that help?
Okay. Yeah, kind of. I'll probably ask my question later about kind of like one of my group members is wanting to do the coronavirus. So I'm just trying to think about stuff that we could put as delays or things like that and what they would fall under.
Okay.
So
Will, I saw you go off mute. Go ahead.
oh yeah, can we give like another example for like a fixed delay? So of course, like something is like being paused at a certain time frame and it carries on to the next. So like in terms of like maybe an epidemic or like maybe a shortage of something, like you can think of like maybe symptoms like appearing in an individual and not like becoming like apparent until like a couple of days after, or like maybe now with like things like supply chain wise and like the economy, like something stopping, like maybe like a package or like maybe aid or like what have you, and then like being manifested later. Does that make any sense? Could that be an example of like a fixed delay in a system? I'd probably have to give you a more specific one, but does that make any sense?
Right. I think it'll help when I get into smoothing delays here next. But yeah, basically, like supply chains are an excellent example. It takes a certain amount of time, say, to get a product from a particular distribution center to my house. And that is usually a fixed delay. We know that that's pretty tightly controlled. It's going to take 2 days for it to get to me. But, and maybe in the case of, say, coronavirus, maybe it takes 14 days exactly for someone to clear the virus if they happen to pick it up. But it might actually be the case that some people clear it in only 7 days, and other
Yeah,
people
or
clear
like
it in 21 days.
Mhm.
And so that type of delay where different people clear it at different times, and so the population as a whole is kind of fuzzier on how long it takes to clear it, that's the next type of delay, the smoothing delay. But if you have a system where you can model it, as you know that if somebody gets inoculated with the virus on day 1, if you know for sure they will have the virus on day 13 and not have it on day 14, that's a fixed delay.
Okay, thank you.
Mhm. All right, any other questions? Great. All right, thanks for that. So, so this is kind of hinting at these things. So our fixed delays down the esophagus, the most important delays in modeling hunger control. I would say that the few seconds it takes for food to get from your mouth to your stomach probably doesn't have a major impact on how quickly you stop eating. What really probably has the biggest impact is how quickly it takes for your stomach to start processing that food. And so there's not only the transport delay in getting food to your stomach, but then there's the delay in how quickly the stomach gets nutrients into your bloodstream, or how quickly the stomach gets signals into your brain to tell you that you're satiated. And so that is where we start talking about these smoothed or averaged delays. And so here I've got an example graph here where we've got the blue line is, say, the input into the stomach, and the red line is, say, the input of nutrients into the bloodstream. And so even though the stomach immediately gets that food, some of the food starts getting absorbed into the bloodstream quickly, but there's a lot of it that's just going to take a while to process. And so that, because there's other processes going on to get them into the bloodstream, you get this very slow rise. And then eventually, once the food moves out of the stomach, you might still, because some of that food is kind of tied up in the intestinal lining and things like that, you might not, or just because those nutrients take a while to become used in the bloodstream, you might not immediately see a drop in nutrients in the bloodstream go immediately to 0. It takes some time for them to go to 0. So this is what I mean by a reshaping effect, where I have a function, an input that looks like a rectangle, but the output kind of looks like, you can understand that there was once a rectangle there, but it kind of got its edges smoothed over. And so this is a type of smoothing delay or averaging delay. And this is also known as exponential damping or exponential decay. And we'll see this directly relates to the toilet example that we've seen before. So you can kind of think of when you flush a toilet, that's kind of like the input into the toilet being, that's that water level. You can think of that water level immediately jumping to saying, I need 15 centimeters of water in the toilet. But the toilet takes some time to actually load up those 15 centimeters. Once it gets up to those 15 centimeters, if you were to raise it to another 2 centimeters, it's going to take a little time for it to get up to that 2 centimeters. So this delay represents more of a sluggishness of the system to respond quickly, as opposed to a simple transport delay. And so, and hopefully this becomes more clear as we move on here. So, so you can imagine us having, so this is what I'm just saying here, that the delay here characterizes not a directly measurable transport delay, but instead an inertia or sluggishness in the system. And so we can model that using a tiny little stock and flow diagram that I'm going to zoom in here on the next slide. And so this little diagram here, basically you'd have an input coming in, and then your output is this stock that I'm calling average. So the input goes in, but we have to wait for this stock here that I'm calling average to respond to that input. So I've got an input going into this flow, and I've got a delay going into this flow, and I've got the average going into this flow. And if I look at the difference between my desired input and my current output average, that gives me kind of a desired change of the, it's how much I would like this average to be changing. But it gets divided by this delay, which is related to that time constant that we were talking about back when we were doing the toilet flow example. So the average is the output, which is like the nutrients entering the bloodstream through the stomach. And they, even though you've dumped a bunch of food into your stomach, you kind of want that food to be in your bloodstream, but the actual nutrients in your bloodstream are much less than that. And it's almost like the difference between the food in your stomach and the actual nutrients in your bloodstream are a driver of this system, but they're getting sluggishly delayed by the process of digestion, which just takes some time. And so that's kind of what we're modeling in this system here. So you could build this tiny little group of this kind of little stock and flow system whenever you wanted to do one of these types of delays. And you might recognize this because this looks nearly identical to the system that you built in the toilet example. So if you remember, your flow rate in the toilet example was the target water level minus the actual water level divided by this time constant, which was that delay. And so our input is the target height and our output is the actual level of water in the toilet tank. The same way our input is the amount of food in the stomach and our output are the nutrients coming into the bloodstream. And so we get very similar patterns here. So basically when we were building that toilet tank, we were building a little delay module that you could use inside models. We can alternatively take this exact same diagram that's over here on the left, and we could draw it over here on the right. And it's exactly the same dynamics, it's just drawn a slightly different way. And this starts looking a little bit like that leaky toilet that I had you guys draw, with maybe some slight, some minor modifications. And so, but again, all I've done is I've taken the input minus average, and that, since it's a minus there, I just turned it into an outflow. So now I have an inflow, which is just input divided by delay, and an outflow, which is just average divided by delay. But this diagram on the right produces the same output as this diagram on the left. And if I were to write the formula for the diagram on the right, then I would get this is the formula that's being implemented underneath the covers of Vensim, or underneath the hood, I guess, of Vensim or Insight Maker. The average at the current time is equal to the previous average minus this dt times average at the previous time divided by delay, plus this dt times the input divided by delay. And and if you see either one of these diagrams in a model that you're building, then you know that you have maybe accidentally or maybe on purpose, but if you didn't happen to notice that you were drawing it, you've implemented a delay. Now, the reason I put these formulas up here is to sort of show why we call it an averaging delay. Because if you take this formula, which is just a representation of the diagram on the right, I can do a little bit of algebra and I get this formula down here. I just can factor out the average, and then I end up getting this thing, which shows the average at the next time step of the simulation is the previous average times this 1 minus dt over delay plus dt over delay times the input. And if you think about this formula, then you can think about this formula as a kind of weighted average of the past value and the current value of the input. So it's kind of like we're saying the next value of this average output is just a combination of its previous value plus whatever input is coming into the system. And we can see here that if we adjust the delay value, which is kind of the sluggishness of the system, we shift the emphasis on whether we're very responsive to the new input or whether we just stick with the old value of the old input. And so in the no delay case, where we say delay is equal to dt, then this dt over delay just becomes dt over dt. So that's equal to a 1. And this 1 minus 1 becomes a 0. So the thing in this underbrace here on the left is just a 0, which means the value of the stock is just going to be the value of the input from just one tiny little time step later. So basically the input nearly immediately shows up on the average, on the output. So this, if you set the delay to the smallest thing possible, which is whatever your time step is in Vensim. So it's like setting your delay equal to 0.01 if your time step is 0.01. then that means that whatever happens on the input will show up basically immediately on the output. So you've gotten rid of all the sluggishness, and you basically get rid of all the reshaping that goes on in this process. But on the other hand, if you make the delay effectively infinite, then this term over here goes to 0. So dt over an infinity basically gets rid of the input's effect on the average. And so the average basically, and then this term over here just basically turns into a 1. And so the average basically never changes. So even though you're changing the input, you're never seeing a change on the output. So setting an intermediate delay kind of creates a smoothed version of these two, where you can leak in a little bit of the input, and it will try to move the system, but the system will kind of stick in its old state for longer. And so you get these smoother responses. So you put a square wave in on the input, and you get something that looks much rounder on the output, because you're averaging the effect of the previous output and the current input. So now with that interpretation, we can view this delay as a kind of average delay. So I mentioned that food can enter the stomach, and there could be a big clump of food entering the stomach. Well, part of that clump will get processed quickly, but another part of that clump might sit around in the stomach for a long time. And if I were to sort of average over all of the tiny little pieces of that large clump of food, then I can view this delay parameter as a characterization of how long it takes a tiny little bit of food in a big clump on average to get into the bloodstream. So some gets in immediately, some takes a long time, but on average, the food gets into the bloodstream after 5 seconds. So some will get in 1 second, some will take 10 seconds, but on average, it's about 5 seconds. So that's one interpretation of why we call this average delay. And so that's what I'm sort of saying here. Food leaves the stomach more quickly at first, but it slows as the stomach empties. So in this case, sometimes people, instead of using the term delay, they use the term mean lifetime. And it's this idea that there is a sort of the food is in the stomach until it gets digested. And when it gets digested, it sort of dies. And so you can say, if the food in your stomach is a population, you can say, how long does that population live? And you can say, well, some of the food gets digested immediately, so it has a very short lifetime, but some of that food takes a long time to digest, and so it has a long lifetime. And so this delay parameter that you put into the smoothing delay is a kind of mean lifetime for the population of food that's in the stomach. It's just trying to get more conceptual models for this delay. And so to get the kind of the last kind of conceptual model here, we can go back to thinking about other ways of that physical systems display sluggishness. And we can go back to something from physics class, Newton's second law. And so, Newton, basically said in his second law, that force equals mass times acceleration, that regardless of how much force you put on a system, it's not going to respond in acceleration immediately or it's not going to respond in velocity immediately because it has mass. Mass sort of slows down the accumulation of velocity. So massive objects take the same amount of force applied to a massive object is going to mean that it's going to take a long time for it to accelerate to a particular velocity. So systems can't change instantaneously, and mass was a proportionality constant that Newton used to say that to capture this effect that things don't change instantaneously with an applied force. So an object's mass represents the relationship between an applied force and the subsequent change in velocity. So if we drill down into that just a little bit, we take F equals ma, something again you might have learned in physics class. We can think about how this applies from a calculus perspective, and we know that acceleration is just the change in velocity over time. So if velocity is a stock, acceleration is its flow. So we can write F equals m dv dt. That's just, dv dt just means the flow going into velocity. And if we do a little algebraic manipulation, we see that the flow going into velocity is going to be whatever force you applied divided down by the mass of the system. So again, mass is reducing your effort to change the velocity of a system. So we can write that in words and saying that change in velocity is whatever force you're applying divided by whatever mass is in the system. And so we're going to come up with kind of a conceptual model of what a mass would be in other sorts of systems, but we're just sort of, drilling back into physics to kind of, to sort of to think about what this means from a physical point of view. And if we make this a little more general, we can say a change in any system variable that we model is going to be whatever force we're trying to use to change that variable divided down by how sluggish the system is. And the fancy word that people use for sluggishness in dynamical systems is inertia. If someone says this system has a lot of inertia, that means that it's going to keep doing whatever it was doing, and you're going to have to put a lot of effort in to make it change quickly. So if you put the same amount of effort in, but you have more inertia, it's going to take longer for the system to change. And so in a physical system, inertia is mass, but really in any system that can be described this way, where you have a desired change, that's this green square curve, and the output is this slower blue curve, then we can characterize the difference between the square curve and the curve, in the softer curve, the hard curve and the soft curve, by the inertia of a system. And so the delay length in simulation is how we're characterizing the inertia. So we're saying that we're going to measure somehow how quickly this rises. And if we can measure how quickly it rises after you put what's called a step into the system, then we can model the mass that's operating in the system, the sluggishness of the system in terms of delay. And so if I put that all together, I've mentioned mass prevents instantaneous changes in velocity. If you heat up a bunch of water, even though you're adding heat, the water doesn't immediately change its temperature. And so physicists have a name for that. They call it heat capacity. Heat capacity, which every material has a different heat capacity, represents how quickly temperature will change if you put the same amount of heat in. So that's a measure of sluggishness. Even something like bucket diameter. If I have a really, really wide bucket, if I trickle in the same amount of water, the height of water in that bucket is going to change slower and slower as the bucket diameter gets big. If I have a very tiny bucket, then if I put the same flow in, it very quickly, the water in the bucket rises. So the diameter of the bucket represents the inertia in that system. And then finally, if we think of social systems, then we can imagine certain groups are going to be more sluggish and they'll be more resistive to change. So there might be some groups that no matter how much education you give them, it takes them a very long amount of time to change their opinions. But there might be other groups that they're maybe you're even very naive, where you tell them anything and they immediately change their opinion. And so we can kind of talk about, as you swing from naivete to stubbornness, then you're actually adding more and more inertia to a system. And all four of these we can model with using a temporal delay. So we don't actually have to model the mass of a baseball or the diameter of a bucket. If we just know how these factors affect the temporal relationship between when we add an intervention and how quickly that intervention is seen in an output, then if we measure the kind of time difference there, then we use that delay as our measure of the kind of stubbornness of these systems. So I can kind of summarize that by saying, for any system you build, we can put the flow of the stock over here as the change in system variable. The force of a change is kind of a desired change in the stock, and we scale that down by the inertia. With a little rearrangement here, we get the desired change in a stock is equal to the inertia times the flow. I just took the inertia and multiplied it by the flow of the stock, and that is exactly F equals ma. I say, oh, sorry, I got a question here. Do I recommend doing modeling something? Do I recommend doing modeling something other than a social system? I think you can model a social system. but I think it's fine to model a social system. I think it's great to build a system of dynamics, how quickly it takes people to change their opinions. And in fact, next week, in I think Tuesday's lecture, we will actually talk about a model of how quickly ideas diffuse into a society after they've been introduced. And so that is a perfect example of how to model the dynamics of social systems. So, you know, wait till next week and we'll see an example of that. And actually, you could argue that epidemic modeling is also that. Also be able to share past student projects. Yeah, I can see what I have in the archive of some good examples of some projects and see if I can post those online. And I can see how that would be helpful. So I definitely think I have some in the archives, and let me dig back through them and see if I can find some good examples. And then I have a couple of like one-line examples in the final project presentation document that's on Canvas, some examples with nutrient flows and things like that. And so you can take a look at those for some quick examples, but then I'll see if I can maybe black out some names and post some old presentations or old reports. I don't want to post too many because I don't want to make it, I don't want to sort of crowd out all of your ideas, because once I've, you know, like we do see reproduction of ideas from semester to semester. And so I don't want to restrict you from rediscovering things that people have discovered in past semesters, but so I'll figure out something. All right. So if I want to summarize all of that, you know, bringing this toilet model back, then we have this basic element here, which is our smoothing delay. And we can then kind of capture that as the desired change in the stock that I've modeled up here in this F equals MA is equal in this model as the input minus the average, the thing that is in the numerator of the flow. And then I model the inertia of the system as the thing in the denominator of the flow, the delay. And then the flow into the stock is that input at minus average divided by the delay, which sort of is just instantiates this F equals MA here. And so we can see that just like this simulates the toilet that we see in the bottom right-hand corner, then we see that the thing that plays the role of mass in like a model of a baseball, you know, flying through the air, then actually models the sluggishness of a toilet to fill up. And so if you have a toilet that can very quickly reach its target water level, then you would have a very small delay here. And that would be kind of like having a baseball with a very small mass, or having a boulder with a very small mass. A boulder with a small mass, if you push on it, it will very quickly speed up. But if you have an old toilet with maybe a valve that's really, really sluggish, that's like having a boulder with a really, really big mass. If you apply a force to it, you might be able to make it move, but it's going to move pretty slowly at first, and it's going to take a long time for you to accelerate it to a high velocity. So any type of system you can think of that has this sluggishness between input and output can be modeled with one of these smoothing delays. So before I get to questions, I just want to give one more concrete example that combines these two delays in one model. So I mentioned the traffic example. So imagine I've got an intersection A. So I've got cars going through this intersection on the left. And then I've got intersection B on the right. And I've got then a stretch of road in between the two intersections, A to B. Now, if I think about cars sitting at intersection A at a red light, the instant that red light turns green, some of them will enter this road section, but a bunch of them have to wait on the cars in front of them to start moving. So they don't all move at the same time. It's not like a fish school. It's almost as if fish have to wait for the first fish to start moving, and then the second fish start moving, and then the third fish start moving. So they spread out over time. And that spreading tells us that we probably should use a smoothing delay. And so I can model this green square curve, the input, represents the time at which the light turns green. That's me saying the civil engineer or the urban planner says at this time we want people to start entering the roadway. And so that's our desired change. But in reality, people start entering the roadway, and so some enter the roadway immediately, but it takes a while for some of them to get in there. And so you don't reach kind of a saturation of how many people will be in the roadway until a while later. And so you get this kind of sluggishness entering the roadway. But once they're in the roadway and they've reached kind of this steady state configuration, they all have maybe a car length or a car length and a half in between them, then they stay pretty much in one formation. Then they start looking like a fish school. So getting from A to B is one of these fixed delays. And so the time it takes for cars to get from the beginning of the intersection or the beginning of the road segment to the end of the segment, we could model with a fixed delay. So you could imagine combining these two things in a model where you've got an input, which is a pulse of cars right after a green light. And then that will end up causing a dynamic variable later to representing the number of cars in the road segment. And then to model the transport delay, you could have another dynamic variable elsewhere modeling the number of cars entering the next intersection. And that will just be a fixed delay version of the cars entering that street block. And then, they might hit a red light, and then this whole thing might start over again. So you could, if you're simulating a whole city, you'd have a bunch of these segments together with a combination of smoothing delays and fixed delays. So are there questions? I think that's my next slide here. Yeah, are there questions about these two delays, the fixed delays and the smoothing delays, maybe in the context of this example or others? Is it clear the two differences between those? So fixed delays are not also the system's inertia. That's a good question. So a lot of times we use the term inertia in a very general way. And if you're just using a colloquial inertia to sort of talk to the average stakeholder out there, I think it's okay to talk about any delay being a kind of inertia. To me, inertia is like the amount of time it takes for a system to change when you want it to change at a particular time and it's not going to change until later. But technically speaking, if we want to be the most descriptive, like what is really loaded up into that term inertia, to me an inertia is a smoothing delay. It says that that it's more than just so a fixed delay is more of, I have a shape of something that enters and I am going to get that exact same shape later. But a smoothing delay says that it's going to enter looking like one thing, but it's going to exit looking like a different shape. And you don't have to add either one of these delays to your model. If you find that your model has an important delay, it's your question to say, what type of delay should I add? But I bet that a bunch of you are going to build your final project models and not have any delays in them. But it's just kind of up to you to decide, are delays important? We might think in the system of modeling hunger control, delays are important because if you eat really quickly, then that might mean you're going to overeat because you're not going to get the feedback signals telling you that you're satiated. But if you naturally eat slowly, then maybe you don't need to model that delay. Or if you have a system that moves very quickly, then like if the only delay in your system is a short transport delay, then maybe you don't need to put that transport delay in. So what you can do is you can always add the delay, and then in Vensim or Insight Maker, change the parameters so you turn the delays down to 0 and see if you get any differences, any qualitative differences in your output. And if you don't really get any qualitative differences as you crank the delays down to 0, then maybe it's okay to just remove those delays. All right, any other questions about fixed versus smoothing? Could I explain the equation with input average delay again? I can. But before I do, I will mention that the next couple of slides explain that in Vensim and Insight Maker, they have a little function which does smoothing delays for you, so you don't have to build this thing. So if you're, I am going to go back for the purpose of this question and look at that equation again. But for those of you that that aren't necessarily following every detail of this, you don't have to worry about it. As long as you understand the idea of smoothing delays, then you'll be able to just put a function in that says, I want a smoothing delay and I want this to be the time constant. So we'll get to that in just a second. But if I were to go back and look at that. Let me see if I can find that, let's say maybe here. All right, so I think this is the equation we're talking about. If it's not, please let me know. But the basic idea here, this is what's been implemented inside Vensim or Insight Maker behind the scenes. And the idea here is that we have two components that could play a role in the output. The average is the output, the average at time t. This is average parentheses t, that's the average at time t. And that we're saying the average at time t is a mixture of the previous average at the previous dt time step and the previous input at the previous dt time step. And what we're basically saying is that delay is telling us how much of the input from the previous dt time step we're allowing to show up immediately on the output, or how much of average are we how much of the previous average are we having show up instead. So if you have a very high delay, then that basically means that your output average at this time step, average t, is going to be pretty much whatever the previous average is, with maybe a slight change from a little bit of the input. But if you really want the input to play a role, you're going to have to leave that input on for a long amount of time, because that input is not going to really have be able to introduce much of an effect on the average. Unless it's on for long. So part of the smoothing delays is if you have very short pulses, then they might actually be smoothed out to the point where you only see a tiny little bump on the output here if you have a large delay. Now, if you have a very short delay, then that's basically saying that the contribution from the previous value of the average at the previous time step is going to be very little on the next value of the average, meaning that the average is pretty much going to follow the input. So even if you had very quick changes in the input, those quick changes in the input are going to show up on the output. So really these smoothing delays, they're actually sometimes called filters. And so we have an input which has a certain shape, and by smoothing it, we're sort of filtering out the things so that we're taking away the fast components of the input and we're allowing the slow components of the input through. And exactly how much of the fast components we're taking away is going to be determined by how we set this delay parameter. Does that help? And if not, are there specific questions I can address? And so this was in response to an earlier question. I'll just pause for a minute here. All right, so I don't see any additional questions. So if more questions come up about this, I'm happy to go back later. So I'm gonna cut to where we were before, which is back, I think it's labeled slide 51. And so now this question is, do we really have to build these structures every time we want one of these smoothing delays? And fortunately not. These are so common that they've already been built for us inside Vensim and Insight Maker. And so basically I can create a dynamic variable inside Vensim. And if I want that dynamic variable to be a delayed version of another dynamic variable called input, I just wire up the input into that dynamic variable. I wire up whatever delay I want. And then I go into the equations for this dynamic variable. And down here under functions, which is we've been kind of ignoring most of the time here, in the Vensim, there is a function called smooth. And smooth takes two arguments, input and delay. And there's also a smooth I function, which is down here, which allows you to also specify that initial condition. So I'm not worry about that right now. So we'll just keep it simple with smooth. And so basically I can put inside this smooth, I can say, well, I wired input up to it, and maybe I'm just going to hard code a delay of 2.5 seconds into here. And this will guarantee that if input is a square wave, then the output will be a smoother version of that. So I'm just put into this function. So input shows up under variables. So that's because I wired it up. And so it showed up here under variables in the bottom right. And then in my equation, smooth input takes this variable and it delays it in a smoothing way by 2.5 seconds. And the output ends up looking like this. So my input, this thing on the left here, was a square pulse. And if I were to plot the thing inside the smooth output, this dynamic variable on the right, then I end up seeing this, this damped version here, where I get this smooth version. So it's not a delayed version in the fixed sense, but it is delayed in that it represents a sluggishness of the bloodstream to take on the food that entered the stomach. So nutrients enter the bloodstream more slowly, and that's represented by this smooth delay. And the delay is the average time until any unit of food gets into the bloodstream. That's what we're simulating there. But if we go to our toilet example, then our input might be the target water level. So, every time you flush the toilet, it's as if you've taken the input from 0 to 15 centimeters, and the initial condition of the toilet is like being at 0. And then so as we've said, well, if you flush the toilet, we've gone from 0 to 15 centimeters, and initially the toilet had 0 in it, then the toilet takes a while to fill, and that's we view as what we call a smoothed version of this change in the input. So delay is the average time until any unit of tank gap gets removed by the rising water level. That's a way to interpret this. And so this here is what the dynamics people call a step response. And so the idea is we put a step. So if we didn't know how to set this delay, you could go into it, you could sit next to a toilet and you could flush it and then use a laser vibrometer or something like that to measure the actual water level of the toilet. And then you could say, how long did it take for a real toilet to clear 63.2% of its final value? So you know the toilet will eventually hit 15 centimeters. So you calculate 63% of 15 centimeters, and then you say, how long did it take after I flushed the toilet for the toilet to come back up to this 63%? And that value here is the so-called time constant of a system, and that's what we use as the argument for this smoothing delay. And so this is our calibration tip for how you move from the real world into the simulation, is that you can find real world data that simulates this step response, and then you can use these step responses to figure out what this delay should be. So, and like I said, the delay is also called the so-called time constant of these systems. With our own models, are we plugging in stats that we find in our research so that it is lifelike and an accurate model? Yes, absolutely. So you build a stock and flow model that represents how you think the system works, but you don't know what the parameters are. So then you might have to go onto Google and Google for, what's the average lifetime of a person in a particular condition? Or you might, if you're modeling a toilet, you might go and flush a toilet and then use a stopwatch and sort of try to figure out how long it takes for it to get to a particular point. And so you can use data that you either gather or search for in order to parameterize your models. So you kind of come up with the structure of the models yourself, and then you make the models more realistic by then choosing those parameters based on data that you can find through the library, Google, etc. Okay.
Yeah, thanks for answering that question.
Great, thanks. So, so this is kind of an exercise here. So I would normally, just for time's sake, because we're in a little slow here, I'll just have everybody stare at this, but we could, do breakout rooms and things like that, and I might experiment with that as we move forward with this for the rest of the semester. But this would normally be an in-class activity where you'd look to your neighbor and you'd ask, what is the time constant of this step response? And what I'm hoping that you'd see is that if I gave you these data that showing you the input was this green line and the output was this blue line, that I just have to say, well, if I go 63% up, that's about here. If you can see my cursor, it's where the 0.63 would be on the y-axis. And if I go all the way over to the blue line, it turns out that that happens around time 3. So from time 1, where the step happened, to time 3, where the output hit 63%, that tells me the time constant of this system is about 2 seconds, 3 minus 1. So that's kind of what we're getting to there. All right, so are there questions about any of that? And then the next step is me showing you the same thing in Insight Maker. All right, so let's see how, go ahead. Yep, question?
Sorry, for our next classes and things like that, could we, like for the first 10 minutes of class or anything like that, like discuss our projects in breakout sessions, or were you planning on letting us do group work in class at all? Or is
Yeah,
that all on the side?
whenever we've had group work budgeted in the normal class, we'll also have it budgeted for the online class. And we can do that in breakout sessions, or you can form every student can form their own Zoom rooms, or however they would like to make that happen. And and I've created a Slack channel as well. So, I mean, we have to kind of improvise, but I do want to make sure that you'll have time to interact with each other and with me. And then on your own time, you're also free to, like if any student goes to asu.zoom.com, you can create your own Zoom rooms and meet with each other in Zoom with video, sharing screens, and those sorts of things as well.
Okay, cool. Just making sure. Thanks.
All right, so let's close this out by seeing how this works in Insight Maker, if that's your preferred tool. So in Insight Maker, very similarly, you can create these 3 dynamic variables like we did in Vensim. You go into the equation for your output variable, and it has, under historical functions, a smooth as well. And it likewise has an input, a delay, and an initial value, just like in Vensim. So I can then set my initial value to 0. It's so in the toilet case, the toilet is initially 0. And then I can set my delay either from an external input, or I can hard code that. And then I can set the input from my external variable. And then likewise, I get the same result that I get inside Vensim. So it works just the same as Vensim. Now, so we want to get, if you want to get a slightly, so the input changes instantaneously, the output changes more slowly. So I do just want to mention that if you want to generate these step responses, just like we talked about generating a pulse inside these models, you can generate a step inside these models. So in Vensim, there's a function called step, where you give it the height of a step and the time of a step. And in the assignment E2 that is available on Canvas, I think as a bonus, I have you generate a step response. And this is how you generate a step inside Vensim. And this is how you generate a step inside Insight Maker. And that allows you to put these inputs in. And then with them, you can generate plots that look like this, where you have an input step coming in, and then you can have an output that's implemented smooth, for example. But you'll notice that inside Vensim, there are other things like smooth 3. These are so-called higher order smoothing functions. And it's basically like putting 3 smooths in series, where each one of them has a third of the delay. So the total accumulated smoothing delay is the same, and the effect of that is, instead of getting this slow rise, you get kind of an even slower rise initially, but then a rapid rise afterwards. And so if we even go to higher order delays, and so there's this smooth in inside Vensim, you can get something that is really, really sluggish initially, and then a really rapid delay, and then a rapid rise, and then it rounds off. And so you can see as the degree of smoothness, so this 20 is my 20th order delay, gets higher and higher, then these smoothing delays start looking like fixed delays. And so that's just, as you see those functions in there, if you decide that you want something in your model that's a little less sluggish, or sluggish in a different way, then you might want to look into these functions. And these functions exist in both Vensim and Insight Maker. And then you'll also notice there's smooth and also delay. And for the purpose of this class, these are synonyms. So smooth in Vensim is identical to delay 1, smooth 3, delay 3, and smooth in, delay in. But there are special cases where your delay number changes over time, where you get different outputs with these different functions. This is an advanced topic that I'm not going to go into, but I just want to mention that you'll see those, and that's the reason why those show up there. All right, so before I round out with this slide of announcements and assignments, are there any other questions? Actually, I'm going to hold off questions. I'm going to stick around. If you would like to stick around for questions after the class, feel free. But I just want to make sure everybody's clear on the announcements and assignments moving forward. On Tuesday, we have Chapter 6 coming up. And I just sent out an announcement that the reading exercise that you normally do at home, well, you still do that at home, but now the reading assessment that you would do in class, you'll also do at home. But it's a time limited assessment, and I'm kind of putting you on the honor code that you'll do it closed book at home. But I give you a little extra time, so you have time to type. So it's 20 minutes, but basically you have to do it by the time we start class, because we'll effectively go over the answers while we're in class. So if you start it 5 minutes before class, it'll automatically submit 5 minutes later. So make sure you start it with at least 20 minutes to go before class. And so then that's already available. The next two, you know, what previously in-class assessments are already available on Canvas.
Can
So again, we've got them.
the day before or earlier than that?
You can complete it tonight if you'd like. They are freely available right now. So then the other assignments I mentioned, there's a reading exercise for E4. Your final project proposal, it's basically a 1 or maybe 2 page document you'll submit as a group. And that's due basically Sunday night. So it's due in a little less than a week. But basically you just have to put down, and all these details are in that final project document. Just give me an idea of what you're doing, what dynamic variables you think are involved. It would be great if you had a causal loop diagram kind of showing me that you put thought into how these dynamic variables relate to each other, but I'm not expecting any stock and flow diagrams. That's kind of the more advanced modeling, but I'm at least want to see that you put some thought into the system that you've picked and a research question that you've picked, that you've chosen. And then assignment E2, that's available, and that again is due this upcoming Sunday. There's some bonus involved in there, and that's just going to give you the ability to play with units, sliders, lookup tables, and delays, so that everybody has some practice with that. And hopefully we have some time on Thursday. If we have some time after class, then we can stick around, and if you want to work on it, then I can be available. And of course, I'm also available at office hours, and I'd be happy to set up an appointment if you need extra help with that. So with that, we're at 4:16, so I don't want to keep you guys any longer. So I'll give you an attendance question now, and I'm happy to stick around if anybody wants to ask any other questions. So the attendance question for today is, what is the term that dynamical systems people use to represent the sluggishness of a smoothing delay? And a hint is the second word in this 2-word phrase is constant. So I'm looking for blank constant. So what is this fancy term that dynamical systems people use to represent the sluggishness of a smoothing delay? And you can submit that as usual. And if you'd like to stick around to ask questions, feel free. Otherwise, I will see you guys on Thursday, and you can just drop off, and I will end the recording here shortly. Thanks always for your patience with this. If you have any ideas for how we can make this smoother, so to speak, then feel free to send me that feedback. Always great to hear that.
Can you repeat that question one more time?
Yeah, the question that I'm looking for is a 2-word phrase. Maybe I can type it in here. So what is a 2-word phrase? And it'll be blank, I'll put in quotes here, blank constant that is used to describe the sluggishness of a smoothing delay. So I just put that in the chat window.
Thank you.
All right, I'm going to end the recording, but I will then still stay online here for anybody who has any other questions.